4.2, what derivatives tell us. We're going to be looking at when we want to plug in x values into a function, and we're going to always assume that x sub 1 comes before x sub 2 in this case, and we want to see which, if we plug it into the function, has a bigger value. If the f of x sub 2 is bigger than f of x sub 1, then we know it's got to be an increasing function. So we would call this one increasing. Oops, increasing. And if it's vice versa of that, if it's lower for its output, we say decreasing function. So right now, all we're looking at is when a function's increasing or decreasing. We're going to use this information, what we know about derivatives and when they're equal to 0 as horizontal tangents. We want to be able to try to sketch graphs. So we have here, we're going to be using We're going to be using this definition of increasing and decreasing that I just mentioned in order to do a couple sketching examples, just given some information, knowing certain things about what values of f of x and derivatives. So I have for example 11, sketch a continuous function f on where it would be an interval of infinity with these requirements for this graph. We want to have its derivative less than 0 on an interval coming from negative infinity to 2. So, okay, means we want to have negative slopes from the left to 2. Then it says we want derivatives of f of x to be greater than 0 or positive, increasing. So it's going to be from the interval 2 to 5. So let's put that down. This will be decreasing. This will be increasing. Oops. And then it says again, we want to be negative slopes from the interval of 5 to infinity. So we're back to a decreasing function. So just knowing decreasing, increasing, decreasing, they're telling me I should have some kind of idea of what this should graph like. So let's see if I have my graph. I see that we're going to be coming from negative infinity to 2. Then we have an increasing from 2 to 5, and then we'll be going on again, so I'm decreasing. So in order to draw this function, knowing that I have to do something here, and knowing I have to do something here, I could draw almost any infinite number of types of graph as long as I follow these decreasing, increasing, decreasing. So I have to be decreasing, I have to be increasing, and at 5 I have to be decreasing. I could draw many, many ways as long as I followed those requirements, and I did. I was decreasing from negative infinity to 2. From 2 to 5 I was increasing, and then from 5 to infinity I'm decreasing. So I've sketched that one. Number 13 tells us we want the value of the function f of 0 equal to f of 4, which happens to also be equal to the derivative at 0, and is equal to the derivative at 2, and is equal to the derivative at 4, and all of these are equal to 0. So what is it telling me? It's saying I've got a point. When I'm evaluating a function, I've got a point 0, 0 I have to go through. I have the point 4, 0 that I have to go through with this function. And then I have turning points are going to be at, I don't know where exactly, but when x is equal to 0, 2, and 4, I've got to have some kind of turning points. The last piece of information on this is telling me f of x has to be greater than or equal to 0. It's saying all the y outputs of this graph have to be 0 or positive above the x-axis. So what I have set up is what I want to do eventually is get to is more of kind of like an interval testing little graph. So that I'm going to put some key points on there. I'm going to put my, when x is 0, when x is 2, and when x is 4, I have to be 0. My turning points. We'll come back to, remember those are called critical points, but we haven't mentioned them yet in the book. But what I have here is I have to go through those points, and if that's the case, that means I have to have f of x doing something on these different intervals in order for it to turn. So I'm probably going to be, once again, you may figure out a different one, but I'm going to say I'm going to have a decreasing, increasing, decreasing, increasing, because the only way I can have turning points is I've got to be a positive to negative or a negative to positive on either side of a certain point where I have a horizontal tangent. So I'm going to have to be this way in order to be able to turn at this point. So knowing this, increasing, decreasing, decrease, increase, decrease, and increase. All right, knowing this, let's try to give a sketch. Knowing I have to go through 0, 0, the point 4, 0. Knowing I have to turn here at 2 and at 0 and at 4. Whoops, wrong one. Sorry. And at 4. I have to turn at all of these. I have to go through these 2 points. If I follow my increasing and decreasing little bar, I should be coming and decreasing and turn at 0. I should be increasing until 2 and turn. And then I should be decreasing and I have to go through this point and turn at 4. And then I'm going to be increasing. So my sketch of my graph with all these requirements would look like this. All right, then moving on. Test for intervals of increasing and decreasing. So we're going to suppose this function is continuous on an interval and differentiable at every point. So that if the derivative is greater than 0 or positive, we know it's increasing. If it's less than 0, we know they're decreasing. So we know all this information now. So what we want to do is our steps is 1, we're going to take the derivative of the function. 2, we're going to plug in a value into the derivative, the f of x prime, and then we're going to check for positive and negative. And 3, we're going to determine that if it's positive, increasing, and if it's negative, decreasing slopes. Okay? So let's go through some examples. I want to do example 17. So number 17 tells us that we have this function of 4 minus x squared. So if we follow everything I just said, if I take its derivative and set it equal to 0, I'll find the points that are my critical points, something's happening. So right now all I know is x equals 0. So if I do my little interval testing where x equals 0, I have to then plug in some value into the derivative in each interval and test. So let's say if I want to be to the left of 0, what if I plug in -1? If I plug -1 into the derivative, -2 times -1 is a positive 2. So it's positive, and we can say it's increasing. And then if I plug a value for the interval on the right side of x equals 0, and I can plug in 1, and I plug it into the derivative, I see that it equals a negative 2. So this negative says it's decreasing on this interval. If I want to go ahead and give a quick sketch, I have that at 0, we're going to go ahead and be turning. But if this, I'm trying to sketch the function, or am I trying to sketch the derivative? The book tells us for number 17, they want us to find the intervals of which f is increasing and decreasing, superimpose the graphs of the function and its derivative to verify your work. So I want to actually sketch both. So if I sketch the function itself, I can see here, let me undo that. The graph of the function, which this is supposed to be going through 2 here, would look like this. This is f of x. And then if I sketch its derivative, it should look like, whoops, I didn't do that one right, like this. So it says here, the function, the increase and decreasing function, it said that I had some kind of critical point or turning point when x equals 0, and that looks true. It says on the left side of the function I was increasing, and then after the turning point I was decreasing. So I do follow this information that we found in sketching our graph.